the electron is moving with a speed of 0.1 c, so it's going pretty fast. The electron is 1 centimeter from the wire. At t equals 0, the wire is attached to a source of potential or a battery, which produces a 15 amp current in the wire in the same direction as the electron motion. Find the force on the electron and describe its resulting motion. Okay, let's get a picture first of what's going on, and then we'll write down the things that we know. So here's our wire. We've got a long straight wire. Here's our electron. It's a little negative charge. It's moving, we'll say, to the right with speed v equals 0.1 c. c is the speed of light, 3 times 10 to the 8 meters per second. Let's put a coordinate system on here. We'll say positive x is to the right, positive y is up, z is out of the page. Okay, so there's our motion, the electron around the wire. At t equals 0, the wire is attached to a source of potential. So we hook our wire up to a battery. And the result of that potential is to make a 15 amp current in the wire. And it says that the current goes in the same direction as the motion of the electron. And what else do we know? The distance between the wire and the electron, normally we call that R. So R equals 1 centimeter, and current is 15 amps. Okay, so we're asked to find the force on the electron and describe its resulting motion. Well, we know that force is equal to QV cross B. Q is easy, it's the charge of an electron, minus E. V is easy, it's 0.1 times C in the x direction, so I hat. We're going to cross that with the magnetic field. Magnetic field we're going to have to find first. So we'll do that next. Let's find the magnetic field. So B equals, and we're trying to find the magnetic field at the electron. So here's our wire, and it's got the current that's flowing to the right. We know that the magnetic field makes big circles around the wire, kind of something like this. We can find the orientation of those circles using our right-hand rule. Our thumb goes with the current. So if this is our wire with the current going this way, we put our thumb with the current, and we see that the circles come around behind and down in the front. So up in the back, down in the front. The place that we care about is right here, right at the top of the wire. What are our fingers doing right here? They're coming straight out of the page. So the direction of the magnetic field right here is out of the page. So we know the direction of B is out of the page. That's the Z direction, or K hat. The magnitude of the magnetic field is given by the expression for magnetic field around a long straight wire, mu naught I over 2 pi r. Mu naught is 4 pi times 10 to the minus 7 Teslas meters over amps. Multiply that by the current, 15 amps, which is a pretty big current, divided by 2 pi times the distance between the wire and the electron, which is 1 centimeters. Put that in meters. And we get the strength of our magnetic field is 3 times 10 to the minus 4 Teslas. There's the size of the field. Field, of course, is a vector, so we'll write the magnetic field as a vector, which is out of the page, or K hat. So let's put this magnetic field in this expression for force, and let's find the force on the electron. So our Q is minus E, V is 0.1 C in the x direction, I hat, crossed with our magnetic field, which is 3. Just to save space, I'm going to drop those extra zeros there. Tesla's K hat. So let's get a little bit more specific. E is 1.6 times 10 to the minus 19 coulombs, multiplying by 0.1 times C times the strength of our magnetic field, 3 times 10 to the minus 4 Teslas, and then we'll leave our vector things at the end, I cross K. So here you might just know what I cross K is, or you might need a little tool to remember it. So I, J, and K we can write in a triangle. If we go against the arrows, I cross k, our result is going to be j hat, but it's going to be negative because we're going against the arrows. So you might just remember that result, or you might use this tool, or you might look it up. Doesn't really matter which way. So we multiply these numbers through on the calculator. We get 1.44 times 10 to the minus 15 newtons. This minus times this minus gives us a plus, and our direction is j hat, or up. So there's the force on the electron. We're also asked to describe its resulting motion. This piece of paper is getting a bit full. I'll just spill onto another sheet. So the resultant motion, let's draw it again. There's our wire. Here's our electron. And let's think about the motion. So we know it's moving to the right. So there's the initial velocity. We know it experiences a force that points up, so there's the force on it. So it's moving to the right, it has a force that points up. The motion is going to be is that it's going to start to drift up or veer away from the wire. So we'll say that it drifts upward. And that's because of the magnetic force that it experiences. It would be difficult to calculate this exactly. We know for sure that we'll have constant velocity in the x direction. The velocity in the y direction, that one's going to change. If you wanted to find the acceleration, you would divide the force by the mass, and it would start to drift up with a certain acceleration that would give a certain velocity. But let's think about that acceleration. The force depends on the magnetic field, but the magnetic field depends on how far away it is. As the electron drifts away, this distance changes, so B changes, so force changes. Calculating that final velocity would not be an easy thing to do. So what we'll say for sure is that it changes because the force is going to change. So it definitely moves up with changing Vy.